All right, let's get started. Welcome, everybody. So it's a pleasure to welcome our first speaker today. So it's Andrei Jaikin from Barcelona, right? Oh no, from Madrid. Wait, sorry, now I'm confused.
From Madrid.
From
Still
Madrid.
the same country.
From Madrid, right? So sorry, from Madrid, and he's going to tell us something about coherence of one-relator groups and the group algebras. Andrei, please.
Thank you. Thank you very much for the invitation. It's a big pleasure for me to speak again in your seminar. So today I want to present my joint work with Marco Linton from Oxford on the coherence of one-relator groups and their group algebras. So let me start with basic definition. So we say that a group is coherent if all its finitely generated subgroups are finitely represented. And we'll say that ring R is left coherent if every finitely generated submodel of R is finitely represented as a left R model. So if we have an ideal, left ideal of R, which is finitely generated, then we can write it represented as a quotient of finite number of copies of R by M, where M is finitely generated. Yeah, and of course, in the same way, we can define right coherence, but in this talk, I will always work with left models, and coherence means left coherence. So the result that I want to present is the following theorem. So is if G is a one-relator group, then in this case, G is coherent. And if K is a field of characteristic 0, then I will show that the group algebra KG is coherent. So the first result is a known problem of bounce luck. And it received a lot of attention in last years. So let me mention the most important cases which were proved previously. The case of one-related groups with torsion were proved by Lauder and Wilton and independently by Weiss. And in this year, Killock and Linton also showed that in this case, you can say more. You can say that they are virtually free bicyclic. So this free bicyclic were known to be coherent. So this is a strong version to be coherent. And in another case, which was known, is the case when the relator is of primitive rank at least 3. So I will not define the primitive rank. I know that it was defined several times in this seminar. Just to mention that so the torsion case is a primitive rank 1, and so the open case was the primitive rank 2. So the second problem, the second result was not studied before. So the coherence is an important property in ring theory because it means also that any finitely generated submodel of finitely presented model is finitely presented. And it implies that the category of finitely presented models is a abelian category. So this property was studied a lot in ring theory, and all results about group algebras that we know comes from results in ring theory. And for example, there are results about amalgamated products of rings or Aichen extension of rings. And if we translate them to results about group algebras, so we have, for example, this consequence that group algebra Kg is coherent if K is commutative Noetherian ring and G is obtained as amalgamation or a chain extension of polycyclic groups. There is another result which was proved by Heneke and Lopez Alvarez. They did not state in these terms, but it follows from the paper that also we know that Kg is the group algebra of a field is coherent if G is free bicyclic. So this is main results which were known before our theorem. So now I will try to explain the main ideas behind the proof. Of course, it's natural to ask whether there is any relation between these two notions, or maybe this is just linguistic coincidence. And in fact, there is a relation. And in order to explain this relation, we have to introduce a third notion, a related notion of homological coherence. So let K be a commutative ring. So for me, ring is always, when I speak about the ring, I always assume that, of course, it has unity, and of course, it's not trivial. So let K be a commutative ring. We say that a group G is homologically coherent over K if every finitely generated subgroup H is of type FP2K. So this means the following. So this means that if we consider the augmentation ideal of KH, so we can so this augmentation ideal is finitely presented. And this is also equivalent to the conditions that if we extend the scalars, this model is finitely presented as KG model. So in particular, we see that if G is coherent, so it implies that H is finitely presented, and this implies, of course, that its augmentation ideal is finitely presented. And also, if Kg is coherent, then this implies that this model, because this is submodel, this is finitely generated submodel of Kg, it can be dependent in Kg, and this finitely generated submodel should be also finitely presented. So homological coherence is a weak version of two previous concepts. Notice that in general, FP2 does not imply finitely presentability. So this is, we know this famous example of Bistvini and Brady, who constructed the first example of this kind. Now we know a lot of examples of different finiteness conditions. So in general, FP2's condition is weaker than to be finitely present. So we can ask whether the same holds for coherence, whether homological coherence is weaker than coherence or is weaker than coherence of group algebra. And it's known some particular cases. For example, Gersten proved that the first question has positive answer for hyperbolic groups of homological dimension 2. Yeah, and also we know that it has positive answer by this result of Bierry's treble, which was generalized recently by Hughes, Killock, Krofoller, and Leary, that it also holds for elementary abelian groups. It's also possible that you can obtain positive answer for B. So in this paper, they consider the case of group algebra over Z, but maybe it's the same method also would give you a similar result of a field. So for these cases, we see that there is equivalence. So once you have cohomological coherence, you also obtain coherence of the group and coherence of the group algebra. So the first step in the proof of our main result is extend this to more general family of groups. This is not really new result. Somehow there are variations of these results in the literature. So, for example, we found some similar result in the book of Dix Dunwoody. Yeah, so the result says the following. Let's construct a class of groups starting from polycyclic groups. And so our class is the smallest class, which contains polycyclic groups. It's closed under finite extensions, subgroups, amalgamations, HN extensions, and direct unions. So in this case, if a group is cohomologically coherent over some commutative ring K, then in this case, it will be also coherent. So this is really nice family of groups. So, and I will present somehow explain the idea behind the proof of this proposition. So in order to see it, we somehow divide C in subfamilies. So we start with the family of locally virtually polycyclic group. And then we construct inductively Cn as locally virtually fundamental groups of graph of groups such that vertex groups are in the previous family. Yeah. So we can observe that these subfamilies are closed under subgroups. And also we have that C is the union of Cn. So we can prove this proposition by induction on N. The base of induction is clear because virtually polycyclic groups are coherent. And so we can assume that we know the proposition for n-1, and we want to extend it for Cn. So we take a group from class Cn, and we assume that it's homologically coherent over K. And now we want to show that if we take a finitely generated subgroup H, we want to show that H is finitely presented. So that without loss of generality, because of this property, we can assume that H is P1, it's the fundamental group of graph of group, where each a vertex subgroup belongs to the previous class. And because H is finitely generated, we also can add some additional condition. For example, that gamma is finite and the vertex subgroup is finitely generated. And so induction hypothesis implies this is finitely presented. So we would finish our proof if we knew that H is finitely generated. So in this case, we would obtain that H is finitely presented. But probably it's not the case, so we need to do small work. And here where this homological coherence of K appears. So the idea is the following. So we can construct a cover of H such that it's finitely presented, and the kernel satisfies the following condition. So it's abelianization when we tensor with K is trivial. So this is exactly the consequence of the condition fp2h, fp2k. So in our situation, basically the same argument shows that we can construct a cover of H, which comes from the fundamental group of graph of group, where we change only H subgroups. So where H subgroups are finitely generated. So this is basically the same construction. And now the point is that if you look at this map, you realize that N intersection with the H subgroup is trivial for any P. And so we know that this implies that N is free. And now together
Is HV or HE, like intersection is trivial?
With HV, with any H vertex subgroup.
Logic subgroups, okay,
Yeah, because here we converse, here the vertex subgroups are the same. The only difference that H subgroups are smaller. We change H subgroups by some finitely generated subgroups because we can do it in order. So this guy will be finitely presented. So it's like this guy is covered. And now N intersects trivially with vertex subgroups, with all vertex subgroups. So it means that N is free. And with this condition, of course, it's like in free group, we don't have trivial abelization. It means that N is 1. N is 3. So basically what we show that we can change H by the fundamental group of graph of groups where each H subgroup is finitely generated, and because HV is finitely presented, this group is finitely presented. So H is finitely presented. So this is the argument. Yeah, and of course this gives us a lot of new examples of groups where homological coherence is equivalent to the coherence. For example, one-relator groups, RAGs, or ascending extensions of free groups. So also we notice that in this famous example of Bistvin and Brady, the group is a subgroup of a RAG. So in particular, the same example does not work. So if we want to construct a counterexample to this question, we need really some new construction, which does not come, which is not similar to construction of Bistvin and Brady. So this is really very interesting question. Yeah. And another application of proposition B is that in our theorem A, the part B, which is says that coherence, this is coherence of group algebra, implies coherence of the group. Yeah, because as I said, For one-relator group, one-relator groups belongs to this class C. So from now on, I will prove the part B. Of course, later I will somehow mention some changes that you can make if you only are interested in part A. So of course, some part of the proofs can be simplified. So any questions so far?
Yes, so this class of groups, this curly C, I mean, it does contain non-coherent groups, right? Already.
Yes, of course. Yes, so the condition, once you belong to this class and you are cohomologically coherent, of course, it implies coherence, but of course, for example, it's contains it.
So I've been trying to think what the simplest examples of non-coherent. Okay, yeah, so something like that.
Belongs to, yeah.
Right. Okay, thanks.
So now we will try to understand this as a part of the proof of this part B. And the first step is this result. Again, it's not new, so the variation of this result appeared in the paper of Kropf-Foller. It's Kropf-Foller, Linnell, and Luke in 2009. So the result says the following. So this is ring theoretical result. So you have a ring. You start with a ring, which you can embed in a division ring, D. And you look at finitely generated left a model of projective dimension at most one. So it means that you have a resolution of M such that this is finitely generated. And both of them are projective. So you have this resolution and induce a resolution when you tensor with D. So you tensor with D over R. You have this resolution. And this exact sequence, sorry. You have this following exact sequence, and now you look at this D dimension of this model. So D is like is division ring, so you can speak about D dimension. And of course, if M is finitely presented, it means that this model is finitely generated. So the model Tor1 is a part of is submodel, is subspace of finitely dimensional D model, and so it's of finite dimension. And the interesting part of the theorem, it says that if once you have that this dimension is finite, of course you will obtain that this model is finitely generated. So this provides you a way to prove that the model M is finitely presented. An immediate corollary of this result is the following. So assume we have a ring K with following conditions. So it has a global dimension 2, which means that for any M, for any model M, you have a projective resolution of length 3. So this is the first condition. The second condition that R can be embedded in a division ring D, as in this case. And the third condition that as write a model, D is of big dimension at most 1, which means that the Tor, second Tor, And so these two conditions implies that I is coherent. So, and the proof is a direct application of this proposition. So we start with some, so we start with the ideal, left ideal of R, and we apply this condition to this model. Now, because of this exact sequence, you can obtain that E is of projective dimension 1, okay, at most 1. And also, when you calculate its torque, okay, the shifting gives you that this is second torque of I, the second torque of M, and this is 0. So we have both conditions from proposition. So here we need finiteness. In fact, we have 0. And the second, we have projective dimension at most 1. And this is exactly what we have here. And the conclusion that M is finitely presented, which means that we prove that I is coherent. So this will be the tool that we want to use for group algebras. So we now R will be a group algebra. We will consider global dimension at most R2 because we will work with groups of cohomological dimension 2. And now I will explain you how to obtain this division ring with this additional property. Any questions so far? Yeah, so our task now is how to construct division ring in order to apply this this corollary D.
So, and for group algebras, basically what it's for locally indicable, are they embeddable into division rings? Like which group algebras, like what is known, which are embedded?
Yes, this is what I explain now. Yes, they will be locally indicable, and I will use the Atiyah conjecture. Yeah.
Okay.
Yes. Yeah, so let me remind you several conjectures on group algebras. So the most famous conjecture probably is the Kaplansky conjecture, which says that if you have a group algebra of torsion-free group of a field, then the group algebra is a domain. And next conjecture is a continuation of Kaplansky conjecture, is a Maltsev conjecture that says that if KG is domain, then it can be embedded into division ring. So Maltsev and Neumann proved this in one special case. So they considered the case when G has a B-invariant order, a bi-invariant order. So they considered this case, and they constructed this, I call it Maltsev-Neumann series. So these are infinite series where coefficients are from the K, and the condition on this infinite series is support of this series is well ordered. So the Maltsev and Neumann prove that if the order is bi-invariant, so this here you can not only sum, of course you can sum, but you can also multiply two series of this kind, and you obtain another series with well-ordered support. And moreover, this ring, this algebra that you construct is a division ring. So in the case of bi-invariant order, it's a division ring. And this produces you embedding of KG in this case to a division ring. And the original question of Maltsev was whether you can extend this result of embedding of KG in division ring when G has only left invariant order. So for left invariant order, you cannot multiply here. So this method does not work. This was, and but for this case, you know that KG is domain. So in this case, you also know that Kaplansky conjecture holds. So this is motivation somehow behind Maltsev fortune. In the case of subfields of complex numbers, we have a strong conjecture, and this is the strong Katia conjecture over K. So it predicts that you can construct this division ring explicitly, and moreover, it will have some very nice additional properties. So let me remind you the construction. So the idea is that the construction is the following. You start with the group G, which acts on L2G, on this Hilbert space, on the left and right. So this action I will define it as lambda, and this is as rho action. And the lambda give us embedding of group algebra of complex numbers to bounded operators of this Hilbert space. And in fact, the embedding lies in a very nice object, which is called von Neumann group algebra, which is the centralizer of in the algebra of bounded operators of image of left action of elements, which centralizer of action with action of right action of G. So right action of G also provides us with a set of bounded operators, and this von Neumann group algebra is the centralizer of this set. And of course, left action commutes with right action, and so group algebra embeds in this von Neumann group algebra. And this object you can embed, so again, this very well studied object, which can be embedded in or localization of this, which we know as the ring of affiliated operators. So this is the ring where we will generate our division algebra. And the Atiyah conjecture predicts that if you start with CG inside this UG and generate, of course, you create the division closure, so you add, of course, all possible sums, multiplication by also the inverses of invertible elements. So Atiyah conjecture predicts that this is this object predicts that this object is a skew field, is a division ring. Yeah. So in this case, the situation can be described like following. So the strong Atiyah conjecture over C, of course, implies Kaplansky conjecture because it embeds group algebra in division ring. Also implies Maltsev conjecture, because this is what Maltsev conjecture asks. Not only for fields of which are subfields of C, you can easily extend it for any field of characteristic 0. And also it provides us with some additional information on this embedding. So it creates us what we call linear division KG ring of fractions. So I will not define what it means. So it's an embedding to a division ring with some very important additional properties. Yeah. Okay. So Atiyah conjecture was studied also a lot. And the result that we need in our proof is that it holds for locally indicable groups. So it holds for locally indicable groups, and in particular for torsion-free subgroups of one-relator groups. So for locally indicable groups, in particular for any field K of characteristic 0, there exists this linear embedding of a group algebra into division ring. Okay, what happens if we consider fields of positive characteristic? And this is a very interesting topic. Of course, you can imagine that all what I said before does not work, because we start here with L2G. So this is Hilbert space, and there is no any analog of Hilbert space in characteristic. But still there is a hope that we can develop a similar theory in this case. So similar theory, I mean that there is a hope that we can prove that at least in the case of locally indicable groups, there exists this linear division KG ring of fraction. And my hope is due to this very important work of Grater, who showed that how to construct this division ring. So he explains that so the ring that will appear is Dubrovin KG ring, which I described now, and basically this is the way to produce this this DKG in the case of characteristic P. So what we have to do, we start with locally indicable group, and we fix. So locally indicable groups are left orderable, but we fixed a special order which called Conradian order. So they have some special orders. I will not explain what this is. There's some additional properties. It's left invariant. It's not, but it has also another additional property. And now, as I said, the Maltsev-Neumann series cannot be seen as a ring. So we only see them as vector, as KG model. So because this is a Conradian left invariant order, there is a natural action of KG on this Maltsev-Neumann series, and we obtain an embedding. This is an embedding of this of group algebra in an endomorphism ring of this space, which I call EKG. And the Dubrovin ring is the division closure of this KG inside this large endomorphism ring, a ring of endomorphisms. So what Grater showed, so she showed the following result. So there exists a linear embedding if and only if this is the Dubrovin ring. Okay, I will call it KG. If and only if the Dubrovin ring is a division ring. And moreover, in this case, of course, moreover, in this case, they are isomorphic. So as KG. So this is complete analog of what we did in this analytic setting. So in this analytic setting, we constructed some huge ring of operators, and inside this ring of operators, we generate a division ring. And now in a characteristic P, we don't have this analog of operators, but we can do it in more algebraic way. And the conjecture says it's also will create a division ring. And the point is that if K is characteristic, of course, you can do the same in characteristic 0. And what Grater says, the theorem of Grater says that in the characteristic 0, because we showed that we have this division ring DKG. So Grater says that this division closure is a division ring, and moreover, it's division ring that we want to find. So we have really an object to look, and the hope that in some point we will be able to prove and answer positively on this question. Yeah. But at this point, as I said, we only know that this division ring, this linear division ring, exists for locally indicable groups only in characteristic 0, and for characteristic P, it's still open. So this will be the main obstacle why the theorem A, part B of theorem A, is only state for fields of characteristic 0. But the rest of the proof is the same. Any question? Okay, so now the next step is to finish, to show that the division ring that we constructed satisfies this additional property that as a right KG model is of weak dimension 1. And this result does not hold for any locally indicable group. Here, it's important that we assume that our group is one-relator group. Or without torsion, we can also assume that it's a torsion-free subgroup of any one-relator group. So, for example, if in the case G is F2 by F2, okay, the linear division ring exists for any K in positive characteristic or in characteristic Z, but is not of weak dimension 1. So this part use that we are working with some special subfamily of locally indicable groups. And now this leads us to proof of theorem A. So I presented only in the case of, for simplicity, only in the case of torsion-free one-relator groups. So assume G is torsion-free one-relator group. So we know that it has a cohomological dimension 2, and this will, as I said before, implies that KG is of global dimension 2. So the argument is the following: is you start with a pre-resolution of Z, and then you take some M KG model, and you tensor with M. With it, and you obtain this resolution of M. And the point is, because you are working with a field, K is a field, this guy, so M is a K vector space, this will be a free KG model. So this is the difference that we need really in this theorem, our assumption on the coefficients that they are from field. For example, the same argument does not work for Z. So ZG is not of global dimension 2. ZG is of global dimension 3. So the same argument could not provide the coherence of this ring. Yeah. So this argument implies that KG is of global dimension 2. Now, as I explained, proposition E gives us this embedding with this property of division ring. Now, the corollary D with these three conditions gives us that KG is coherent. In particular, we saw that it's homologically coherent over K. And now the proposition that I started shows that this also implies that G is coherent. Okay, so this is the proof of two parts of the theorem, but of course you may ask whether if you want to prove only the part A, something can be simplified, and this is the case because of course when you work with groups, subgroups, you only have to look in submodules associated to groups. And so, for example, assume that we in this situation, so we in the situation of G is in class C, homological dimension 2, and satisfies strong Katia conjecture, for example, locally indicable. So proposition B and C imply that in order to show that if that G is coherent, it's only we only have to look and ideals, left ideals coming from the group, from the argumentation ideals of the subgroups. And in particular, we need to show that these numbers are finite, but these numbers, of course, we know that these numbers are the second L2 Betty numbers of H. So if you are able to show that second L2 Betty numbers of subgroups are finite, you also would conclude that you can apply the same method, and if G satisfies this condition, you would obtain that G is coherent. And in particular, in this way, you can obtain these two cases. So assume that G belongs to one of these two families, fundamental groups of two complexes with non-positive immersion. So I will not define it because I know you will have another talk where Danny Weiss will, of course, will define it and explain what are these groups. And another family is groups where of cohomological dimension 2, satisfying the strong Katia conjecture over Q and having trivial second L2 numbers. So the point that here in the first case, so this non-positive immersion implies that is always finite for any finitely generated subgroup. And in the second case, in fact, you can show that it's always 0 for any finitely generated subgroup of G. And so, as I explained before, it implies that G is homologically coherent. And if additionally you assume that G is in the class C, it will give you that G is coherent. Okay, let me finish the talk presenting a few questions. So one of the questions that naturally arise is of the relation between these two notions that I mentioned before, these notions of non-positive immersions and having trivial second L2 Betti number. And it would be interesting to decide whether this is really equivalent for compact aspherical two complexes. At this moment, we don't know this. Another interesting question is, okay, we saw that the triviality of second L2 Betti numbers helps to prove coherence of the groups. Yeah, it's like in this case. Yeah, but the natural question whether coherence implies already this condition. And there are here probably the answer is no, and there are many examples to look. And just I want to mention one old example, old question of SER. So whether the group SL2 Z1 over P is coherent. So this group is a lattice. So this group is a lattice in SL2A times SL2QP. And there is another lattice here, which is F2 by F2. And there is the theory of Gabor-Yu provides that once you have two lattices in the same locally compact group, then the vanishing of L2 Betti number is invariant. So of course we know that the first L2 Betti number is here 0, and the second is non-zero and second. And so it's the same way. It will be implied, this is G, it will imply that the second L2 Betti number of this group G is the same as Euler characteristic. So it's not 0. It's not 0 in this case. So of course, it will be very interesting to decide whether this group is coherent, because if it's coherent, this question has a negative answer. Okay, this was what I wanted to say. Thank you.
All right, thank you very much. Thank you. Are there any questions for the speaker?
Could you repeat about L2 Betti numbers for two lattices? Like you said that they vanish simultaneously, like here in the last question.
Yeah, so it's measurable. So these two groups are measurable equivalent. It's the notion of Gabor-Yu, and two measurable equivalent group. So the vanishing of L2 Betti, so the L2 Betti numbers, there is a positive constant such that one L2 Betti numbers are another by this constant. So the vanishing is invariant. So they can have different, of course, L2 Betti numbers, just go to a subgroup of finite index, but the proportion
So
is
they all differ by a constant, like
the proportion is the same.
Interesting.
So it's easy to see, for example, for subgroups of finite index. So this is, but also when you have two lattices which are not commensurable, and this, so this is a theorem of Gabor. Yeah, you have the same. Of course, these two lattices are not commensurable; they are completely different. But they have this property.
Okay. Thanks.
All right. Any other questions or comments? So I had a question. It's the arguments or the proofs that you were describing, the arguments are very algebraic, but still. So coherence, it also has an algorithmic version. So there is a question about effective coherence, at least for groups. I think for algebras, one can also ask this question whether or not, if you know, once you know that something is coherent, let's say a group, whether there exists an algorithm which, given a finite subset in a group, actually finds a presentation for the subgroup generated by this subset. I mean, it is a much more difficult question, but I was wondering whether there are sort of any classes here where there might be any hope of approaching this question, saying something meaningful about it.
No, I don't know really. Really, this theorem, yeah, okay, this part, yeah, when yeah, so maybe this can be done. Yeah, it's somehow it's constructive proof, but of course, yeah, it's okay. I don't know. Yeah.
Okay, all right.
Mhm.
Okay. Any other questions or comments? All right. If not, let us thank Andrei again. Thank you. It was very interesting. Okay, so I'll stop the recording now.